Continuing on, example 3 says use division to verify that x plus 4 is a factor and factor the resulting quotient. So because we need to verify, what we could do is we could use this factor theorem and see if we get 0. But because I need to go on and factor the resulting quotient, I need to go ahead and just divide it out. So can I use synthetic division to divide with x plus 4? And the answer is yes. You can use long division, but synthetic will work. So we're going to do a -4 on the outside. I have x cubed, x squared, x and constant, so I'm not skipping any place value, so I don't need any zeros. So we'll put 2, 5, -14, and -8 in here. Okay, when we use synthetic, we're going to bring this first one down and then multiply, add till the end. So multiply, add, multiply, add, multiply, add. So this right here with a remainder of 0 means that we have verified. So that is a quotient. So now what do we have left? If my remainder is 0, this is my constant, my x, and my x squared. So we have 2x squared minus 3x minus 2. So we need to factor the resulting quotient. So we have a trinomial. So for trinomials, do we have a GCF? And we don't. So now let's go into our x. My a times c is 4 times -2. My b term is -3. So what adds up to b but multiplies to ac? Pause the video if you want some more time. We get -4 and 1. -4 times 1 is -4. When I add, we get to -3. So I cannot just say this factors to x minus 4 and x plus 1 because x times x does not give me a 2x squared. Because this is a hard trinomial, meaning my a is not 1, we need to rewrite this middle term. So now we have 2x squared minus 4x plus x minus 2. What I did is I rewrote this middle term using these numbers here. And if I combine these back together, -4x plus x gets me back to -3x. So I haven't changed this at all. I've essentially unsimplified. I've broken this term into 2 terms. And now that I have 4 terms here, I can factor by grouping. So my GCF in this first group is 2x. So we'll pull that out. And that leaves me with an x minus 2. My GCF in the second grouping, notice that this already matches this. So my GCF is 1. There's nothing I can divide into x and -2. So we're going to pull out a GCF of 1. And I need that 1 so I know what to pair this 2x with. So that leaves me again with x minus 2. So my GCFs make my first binomial. We have 2x plus 1. And then notice I have x minus 2 twice. So that's my second binomial. Now, I'm pretty sure in my math lab, this is what it's looking for. It says use division to verify, and then factor the resulting quotient. So this is the factor of the resulting quotient. Okay, so this is what my math lab is looking for. But as a little bonus right here, let's make a better arrow real quick, sorry. Okay, as a bonus, and this is what we're going to be doing this lesson. This polynomial, 2x cubed plus 5x squared minus 14x minus 8. This equals 2x plus 1, x minus 2, and x plus 4. So a lot of times when I'm teaching this in class, I get, well, where did this x plus 4 come from? And that's what we originally divided out. So that x cubed means I need 3 different factors. And here are my 3 different factors. This right here was this quadratic, but here we have a cubic. So we have 3 different factors. This is what I have to be able to do by the end of the lesson. Now, this one was nice to us because it told me the first thing to divide out. So once I divided this out, now I have a quadratic, and now I have ways to solve quadratics. We can solve by factoring, by the square root property or method, and by the quadratic formula. But I have to take this cubic, or in one problem, I believe we're going to have a quartic, and next to the fourth, we need to be able to divide it out enough to get down to an x squared so that then we can have our 3 methods to handle it. So what happens when I am not given this first factor or first 0 to divide out? And that's where this next theorem comes into play, our rational zeros theorem. Our rational zeros theorem says, given a polynomial p of x, the potential rational zeros are in the form of factors of a naught or a sub 0 over factors of a sub n. So what does that mean? My a naught is this back constant right here. And then my a sub n is this leading coefficient. Now, a lot of times, and I think even if you use your Ask My Professor or view an example, it's going to use P over Q. So P goes with this back constant, and Q is your leading coefficient. And so this is the same as P over Q. So let's use this here. Example 4. Use the rational zeros theorem to list the potential rational zeros of a polynomial function. Do not attempt to find the zeros. So what I need to do is I need to list my factors of P as I write Q, my factors of P over my factors of Q. P is 4, so my factors of 4 are 1 times 4 and 2 times 2. And you can list these in any order you like, but I usually like these in ascending order. So I'm going to do plus or minus 1, plus or minus 2, and plus or minus 4. Okay, but that can be in any order. And I do need plus or minus because to get to this 4, for example, we can do 2 times 2. So positive 2 times positive 2, or negative 2 times negative 2. I can do positive 1 times positive 4, or negative 1 times a negative 4. So we need both signs in there. And then my Q is this 3. So the factors of 3 are just 1 times 3 since that's a prime number. So now what I need to do is I need to divide everything in the top by everything in the bottom. So I'm going to start by dividing everything by 1. If I do 1 divided by 1, we get plus or minus 1. 2 divided by 1 is plus or minus 2. And 4 divided by 1 is plus or minus 4. So I like to just kind of make a little check under that one. I know I've divided everything in the top by that 1. So now let's move on to 3 and divide everything in the top by this 3. So 1 divided by 3 is plus or minus 1/3. 2 divided by 3 is plus or minus 2/3. And 4 divided by 3 is plus or minus 4/3. So this is my list of potential rational zeros. How many potential rational zeros do we have? Well, we have 2, 4, 6, 8, 10, 12. I have listed a possible 12 potential zeros. Now, I want to make note that I'm not going to be using all of these right here. Okay, this is all going to come together as we go through more examples, but I want you to understand that I have 12 potential, and I should put 12 potential rational zeros. Let me go ahead and put rational. Okay, but when I have an x cubed, that has a degree of 3 as a bonus right here. My maximum number of zeros is 3. And these maximum number of zeros include rational and irrational, real and complex zeros. And I have a potential of 12. So what this does right here is it gives me a good starting point. There is an infinite number of solutions that we could technically have to plug into here, or maybe not solutions, but an infinite number of values that I can plug into this x. And I know that only 3 are going to work. So it takes our infinite pool of numbers and it dwindles it down to 12. Now that's still not a small number, but it's a lot better than infinite, right? And if we didn't have our calculator, that's where this factor theorem would come into play. I would have to one by one plug in my values into my function until I got 0. And once I got 0, I would know that that is a factor. Now, thank God for calculators that we don't have to do that 12 different times. But that is why this factor theorem and this remainder theorem kind of go into this unit. If we didn't have calculators, we would now take those 12 potential rational zeros and plug them in and see if any of those were factors. But we're not having to do that. We are just listing our potential rational zeros. So all of that to go to the next one. So now let's list our P over Q. Our P is 9. So that is plus or minus 1, plus or minus 3, and plus or minus 9. 1 times 9 and 3 times 3. And then my Q is the 6. So we have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. 1 times 6 and 2 times 3. So now we're going to divide everything in the top by everything in the bottom. So let's start with this 1. 1 divided by 1 is plus or minus 1. 3 divided by 1 is plus or minus 3. And 9 divided by 1 is plus or minus 9. Check. We have divided everything in the top by 1. So now let's move over to 2. 1 divided by 2 is plus or minus 1/2. 3 divided by 2 is plus or minus 3/2. And 9 divided by 2 is plus or minus 9/2. So check, we've divided everything in the top by 2. Now let's move on to 3 and kind of be careful when we go forward. 1 divided by 3 is 1/3, and I don't have that already wrote. So we can write plus or minus 1/3. And now 3 divided by 3 is 1. I already have that, so I don't need to write 3 over 3 because that's 1 and it's already here. 9 divided by 3 is 3, and I also already have that one. So we are done. When I divide by 3, we only got one new potential rational zero. Then lastly, 6. 1 divided by 6 is 1/6. I don't have that wrote yet. 3 over 6 is the same as 1/2. That's already wrote, so we're not writing it again. And 9 over 6 is 3 over 2, and I already have that one as well. So from dividing by 6, we only got one more potential rational zero as well. So here is my list of potential rational zeros. How many do we have this time? 2, 4, 6, 8, 10, 12, 14, and 16. We have 16 potential rational zeros. As a bonus question, what is the max number of zeros that I have? And here we have a degree of 4, that is x to the 4th. So we have a max number of 4 zeros. I have 16 potential rational zeros, and one of these could work, 4 of these could work, or honestly, none of these could work. We could have 4 different solutions that are maybe complex, meaning imaginary solutions, or irrational, meaning we have square roots in them. But this is my starting point. So again, if I didn't have a calculator, I would then apply my factor theorem and plug in those 16 numbers and see if I ever get a 0 when I substitute those in to this equation.